there. I invite you to apply for the PG Diploma program in Data Science by IIIT Bangalore in collaboration with
Good evening, dear students. Welcome to Ekeeda. I am Dr. Deepak Khurana and I am the faculty for Strength of Materials. Today in this lecture, we are going to study the topic bending of stresses. Right? So first we will discuss some summary that summarize the bending stresses, formula to be used in the calculation for GATE exam. And then later on, we will discuss some numericals based on the GATE questions or the questions asked in previous GATE exams. So let us start the topic. So our topic of interest is bending stresses. So what is bending stresses? And but before that, you must study the shear force and bending moment diagram, because you won't be able to study the bending stresses without knowing the bending moment and shear force diagram of a beam, right? So we have beam, you already know we have different type of beams are there, cantilever beams are there, simply supported beam is there, fixed beam is there, right? So different beams are there, different type of loading is there in the beam, isn't it? So based on that, we are going to study now the bending stresses, right? So suppose you have a beam. You have to go to the theory lectures. I'm just taking a summary of the bending stresses in this lecture. Suppose this is a simply supported beam. This is a simply supported beam. And load is applied. Load is applied. The bending moment will be developed all around the length of the beam, right? Bending moment will be developed. And now we want to find out the bending stresses, right? It may have different cross-section area. It may be rectangular cross-section area. It may be square, or it can be circular cross-section area, whatever is the cross-section area, right? So the bending equation, you have to go to the theory lectures. That bending equation for any type of beam where there is a pure bending, the assumption is the assumption is that there should be pure bending. Although there are shear forces, but the shear forces are very small as compared to bending stresses, so that shear forces can be neglected while calculating the bending stresses, right? So shear forces are neglected. Shear forces must be neglected. And there are other some of the assumptions are there, that material should be homogeneous and isotropic. Material should be homogeneous and isotropic. Means it should have constant properties throughout the material, right? Pure bending should be there, and the modulus of modulus of elasticity, remains constant. So based on these assumptions and two, three more assumptions, that the cross-section area before and after the loading should be same, right? So one more assumption is there, that transverse sections before and after loading remains constant, right? Assumptions related to this equation. Based on these assumptions, in theory lecture we had derived the bending equation, right? And that bending equation is given by m by y equal to E by R, right? M by I, sigma by y, E by R, right? Here m is the, what is m here? M is the bending moment at a cross section of the beam. I is the moment of inertia. Sigma is the bending stress. This is the main thing which we want to find out, right? Bending stress. And y is the distance of fiber where we want to find out bending stress from neutral axis. E is the modulus of elasticity. And R is the radius of curvature. So these are the values, m by I, sigma by y, E by R. And from here, we can find out the stress at any point of the beam, right? So suppose we have a beam. Again, I'm making a beam here. Suppose this is a rectangular beam. It is simply supported, right? So the cross-section area is rectangle. Yes, and here it is neutral axis. Right? This is our neutral axis. And we want to find out the bending stress at this point. Suppose at this fiber, suppose EF, we want to find out bending stresses, and it is at a distance of y from the neutral axis, right? In that case, the bending stress will be given by m by I equal to sigma by y equal to E by R. So stress will be equal to, if we combine this equation, and we know the bending moment here, so sigma will be equal to my by I, right? My by I. And you can see here, m is constant at a certain point, at a certain cross section. If m is constant, I is constant, sigma is proportional to y. As the y increases, the bending stresses are also increasing. So as the y increases, bending stresses are increasing. So at suppose the maximum fiber is at a distance of, this distance is suppose d by 2 from the neutral axis, right? And total depth of this fiber is d. Total depth of the beam is d, and outer fiber is at d by 2 distance. So at y is equal to 0, based on this equation, at y is equal to 0, sigma will be equal to 0, and at y is equal to d by 2, sigma will be equal to sigma max, and that will be given by m by I into d by 2, and this is sigma max, right? The value of y is d by 2 at the outer fiber. This is the outer fiber. y is equal to d by 2 means that this is the outer fiber. It means that bending stresses are maximum at the outer fiber. So bending stresses are maximum at outer fiber. And also we know that from this equation we know that the variation is linear, and variation of bending stresses is linear. So from here we can draw now the bending stresses. So bending stresses will be a linear variation like this. Bending stress is a linear variation, and it is maximum at the outer fiber and 0 at the neutral axis, right? Here it is 0 and here it is maximum. Right? On one side it will be compressive, on another side it will be tensile. So this is the maximum stress at the outer fiber, and at the center, at the neutral axis, the bending stress will be 0, right? So this is how we find out the bending stresses. My by I is the equation for bending stresses, and the variation is linear. This should be remembered while solving the bending equation, right? Now you should remember that some of the diagrams for bending stresses, like suppose if this is a rectangular section, as we already discussed, rectangular section, I'm making now separately. The bending stresses will be like this. So this will be the bending stress equation diagram. So this is bending stress diagram, right? And if it is hollow, this is the this is solid rectangular section, right? I'm writing here solid rectangular section. And for hollow rectangular section, so this is hollow rectangular section like this. Now it is hollow. In that case, what will be the diagram for bending equation? Hollow rectangular section. For hollow rectangular section, you will see the bending stress, because inside there is no material. In the hollow part there is no material, so no chances of bending stress in that part, right? So this will be a straight line. So if I draw the bending stress for this case, this is a straight line, simply a straight line between hollow section, and then this is the bending stress. This is the bending stress. Bending stress will be varying only on the solid part, right? This part. Right? So this is the curve for bending stresses, and inside there is no bending stress, only this is a straight line, because there is no material, so no stresses will be developed, or stresses will be developed at the outer fiber only, and here at outer fiber this will be sigma max, maximum bending stress, right? This is the case for hollow sections, right? Similarly, we can have a solid circular shaft like this, This may be a solid circular shaft. The cross section is circular and solid. Again, according to this equation, m by I sigma by y E by r, based on this equation again, the bending stresses will be maximum at the outer fiber of this section, like this. So this is the variation of stresses in case of a hollow solid circular shaft. This is a solid circular shaft or beam, right? And there may be hollow circular shaft or circular beam, like this. This is hollow. Like this, right? And because inside hollow, so there is no material, so no point of stresses inside the hollow section. And again, the stresses will be only in the material outside the hollow part, right? So this will be the variation, right? Like this. So this is the variation in case of hollow circular shaft. Right? So this is how the variation, this is the variation of the bending stresses in case of solid rectangular, solid circular and hollow rectangular, hollow circular sections, right? And you can see here in all, the stress is linearly varying based on this equation my by I, right? So this is the equation and the stress is proportional to y, right? So this is the basic concept. Now in this equation we want m and I. That is important. We have to find out m and I. So we have to find out the bending moment now. So you have to go to bending equations, shear force and bending moment diagrams, and you should know what is the bending moment diagram for the particular type of beams, like simply supported beams, right, or fixed beams, or cantilever beams, right? So let us take a case of cantilever beam. When a load W is applied, what type of bending moment was this? L length is there. So you should remember that. I'm just making a glimpse of that. This, right? This is the bending stress, bending moment in case of cantilever with point load. So this is WL. So M max in this case will be WL. Why we need M max, maximum bending moment? Because the stress depends on My by I. And if M is maximum, in that case, sigma will be maximum. So we want both maximum, M max and Y max. The failure may take due to maximum bending stresses, right? The maximum bending stresses will occur when there is maximum bending moment and outer fiber, Y max, right? So we want basically for maximum stresses, because failure takes place at maximum stresses, M max. This is important for us, maximum bending stresses, right? So in this case, in particular this case, cantilever beam with point load, WL is the maximum bending moment, which will be used to find out the maximum bending stresses, right? Similarly, let us take a case of UDL with cantilever beam. So this is a UDL, W kilonewton per meter, and this is a cantilever beam. And what type of bending moment diagram was there? So bending moment diagram for this case was like this. This was a parabolic curve in negative direction. You have to go to theory lectures to see how we got this curve. This was the curve bending moment diagram. So this is the bending moment diagram. And what is the value of maximum bending moment in this case? In this case, what was the maximum bending moment? Mmax. Mmax. So Mmax was at the at L is equal to 0 at the fixed point, and that was equal to WL square by 2. WL square by 2. L is the length. So Mmax in this case was WL square by 2. You should remember this thing also, right? Let us take one more case. Simply spotted beam with point load. I am taking the case of simply spotted beam with point load. What was the bending moment diagram for that case, right? Just you should remember that. So what was the bending moment diagram for this case? This is a reaction RA. You should remember RA. The reaction at B was RB, right? You can solve it using the hogging or sagging bending moments, right? And the bending moment was maximum at the center. Suppose this is center C. So maximum bending moment was occurring at this point, at center point. It is increasing and then it is decreasing, and this is the maximum bending moment. This is our Mmax. Mmax. Why we are finding Mmax? Because the failure takes place due to maximum bending moment, right? So Mmax in this case was equal to WL by 4. WL by 4 if W is the point load. This was the maximum bending moment in case of simply spotted beam with point load, right? And let us take last example. Simply spotted beam with UDL, and then we will be able to solve the questions on this. So summary of the theory will be over now. So W kilonewton per meter. So this is the UDL acting on this simply spotted beam. And what was the bending moment diagram? This is bending moment diagram. What was the bending moment diagram for this case? You should remember that this was a parabolic diagram. First it was increasing and then it was decreasing like this, right? And maximum bending moment was at the center again. This is center. So at C point, at center, the bending moment was maximum. So this is Mmax. So in this case, Mmax is given as WL squared by 8. WL squared by 8 for this case, right? So these are the some of the diagrams to find out the maximum bending moment, right? If the different diagram is not symmetric, then you have to find out the bending moment using the definition of the how to find out the bending moment, right? So let us proceed now. Let us solve some questions based on this. Take this question now. What is this question? A simply spotted beam of width 100 millimeter. Width of the beam is given 100 millimeter and height is 200 millimeter, right? So this beam is given to us, and this is rectangular beam. It is given. Height is given h. Say h is the height, that is 200 millimeter, and width is also given. Say b is the width, and this is 100 millimeter, and this is a rectangular beam, right? 200 by 100, and solid rectangular section is there, right? Solid rectangular section is there. Length is given to us, that is 4 meters. It is carrying a uniformly distributed load. UDL is there. You can see here. This is UDL of 10 kilonewton per meter. This is UDL. Uniformly distributed load on the entire section of the simply spotted beam. 10 kilonewton meter. The maximum bending stress in the beam is, what is the maximum bending stress? What is the maximum bending stress? That we have to find out, right? For maximum bending stress, you have to look for two things. One, we know the formula that m by I equal to sigma by y equal to E by R. And solving this, you will get sigma is equal to, one part of this equation can be taken, that sigma will be equal to my by I. If you want maximum bending stresses, because the failure takes place due to maximum bending stresses, right? If you want sigma max, in that case, bending moment should be maximum and y should be maximum divided by the moment of inertia. Moment of inertia is constant because the area is constant, right? So m max. Now for m max, you should know the bending moment diagram of the simply supported beam, and bending moment diagram for simply supported beam for this case is, we have just seen the bending moment diagram is a parabolic curve like this, parabolic curve, right? And it will be maximum at the center, maximum at the center, m max, and this m max is given by, this is our bending moment diagram, and that will be given by WL square by 8, right? Length is 4 meters and W is 10 kilometer per meter. So this is 10 multiplied by 1000 to remove the kilo, so that it may be in SI unit. L, length is 4 meters, so 4 square by 8, right? So this is the WL square by 8, whatever is the value, right? This is the M max. Now we want Y max, right? M max is there, Y max. What is Y max? Now we want Y max. Y is the distance of the outer fiber. Outer fiber. This is Y max. This is basically the Y max, the outer fiber. Right? So this is Y max, and the variation will be linear. Variation will be linear like this. Right? So this is the variation. Next, right? So this is the maximum bending moment. Linear variation, sigma max. So sigma max, for sigma max, Y max is basically h by 2, half of the total height, and h is 200 millimeter. So this is 200 by 2. So this is 100 millimeter. 100 millimeter. Now we can find out sigma max. So that will be m max, which is WL square by 8, into Y max, which is h by 2, and divided by I. Now, what is the moment of inertia of a rectangular section? I. Moment of inertia of a rectangular section. What is the moment of inertia of a rectangular section? That is BD cube by 12 or BH cube by 12. Right? About neutral axis. We are taking about neutral axis. Right? BH cube by 12. So put here the value BH cube by 12. Isn't it? Solve it and you will get the answer. What is the maximum bending stress in this case? And the sigma max will come out to be, I'm writing directly the answer, that is 30 megapascal. Solve it and you will get, values are given to us. W is given, L is given, H is given, B width is given, right? So 30 megapascal, this is the answer of this question. So this is how we can find out the maximum bending stress in case of any beam, right? So for maximum bending stress, because the failure takes place at maximum bending stress, you need to find out two things. One is the maximum bending moment. You have to locate the value of magnitude of maximum bending moment first, then the maximum fiber where the maximum bending stress occurs, and that maximum fiber is the outer fiber basically, right? The maximum distance from the neutral axis, right? And then I, you have to locate what is the value of I. If it is circular section, then this is pi by 64 d to the power 4. If it is rectangular section, that is BDQ by 12. For other section, you may have to calculate the moment of inertia, right? I. You have to go to the theory lectures, how to find out moment of inertia of the different sections, right? So this is the way of finding the maximum bending stress. Let us take one more example. In this question, it is given that a cantilever beam is there, right? This is cantilever beam, figure is also given to us. This is cantilever beam. Cantilever beam has square cross section. The cross section area is given square, that is 10 millimeter by 10 millimeter. Dimensions are also given 10 millimeter by 10 millimeter. It carries a transverse load of 10 kilonewton. The load is also given. This load is given to us 10 kilonewton. Considering only the bottom fiber, we are considering only bottom fiber, right? Only bottom fiber, this fiber. And you know that the bending stresses are maximum at the top or bottom fiber, right? Because this is the at a maximum distance from the neutral axis, right? So basically, we are looking for Y max. This is Y max basically, right? This is our Y max. Bottom fiber. When we say bottom fiber, it means this is Y max. Means whatever stresses will become, that will be maximum stresses. But the bending moment should be maximum for that. Bottom fiber of the beam. The correct representation of the longitudinal variation of bending stress is how the bending stress is varying, right? We already know that M by I, sigma by Y, E by R. In that case, stress is My by I. Now in this case, Y is fixed. Y is fixed. Y is maximum because it is bottom fiber. So at bottom fiber, Y is basically the Y max. The distance of the maximum stress, maximum fiber, right? Y is Y max. I is also constant, but that becomes constant now because we are looking for only the bottom fiber. I is also fixed, or you can say constant, because I is same because the cross section area is uniform, and that is BDQ by 12, right? Now M, so sigma is now proportional to M. If M is varying, sigma will be varying. Whatever is the variation of M, same will be the variation of stress, right? And the stress is given by this equation. So basically, we have to find out the variation of M. And the same will be variation of the stress, sigma, right? So this is the concept here. So this is our beam. I'm making beam as a line here. Although beams are never a line, but for simplicity, we are making a line here. And this is a 10 kilonewton load is applied here. 10 kilonewton load is applied. And it is at the center. And free end is free and no load is there at this end, right? So this is suppose A, this is B, and this is C. And we have to draw the bending moment. Based on that, we can draw the bending stress variation, right? So this is 1 meter. 1 meter. Distance is given to us 1 meter and 1 meter. So what will be the bending moment diagram? So you can take a section to find out the bending moment. You can take a section here at a distance x from the free end. And what will be mx? Mx. Moment of all the forces to the left or to the right of the section. And to the right of the section, there is no force. So there is no moment. So mx is 0. And this will be valid from B to C. So this equation is valid from B to C. Right? It means that at B point, bending stress is 0. At C point, bending stress is 0 because there is no load there. Right? So it will be a linear variation. So if I draw, so up to B to C, so this will be zero variation, right? So there is no variation in bending moment from B to C. So this is B and this is C and zero bending moment. Now proceed further. Take another section. Now we can take one more section here. Let us take a section between C to A. What is happening between C to A? So let us take a section here now. Between C to A. So let us take a section here at distance x from the free end. This is our free end. So for free end, that mx will be equal to, load is 10 kilonewton. So this is 10 multiplied by, moment of this load will be 10 multiplied by x minus 1, right? So because this distance is 1 meters. So this is x minus 1. So this is 10x minus 1, isn't it? And this is a linear variation. And this is a linear variation. So at C point, where the value of x is 1 meters, x is equal to 1 meters, put here x is equal to 1 meter, so MC will be equal to 0. And at A point, where x is equal to 2 meters, put the value of x is equal to 2 meters, you will get M will be equal to 10 kilonewton meter. And the variation is linear. So this is a linear variation. Like this, right? Straight line. And it is increasing from C to A. This is A point, and this is the M max, right? So this is the variation of the bending moment from C to A, and this is a straight line, linear variation. Linear variation. And M max will be equal to 10 kilonewton meter. 10 kilonewton meter, right? So it means that the answer is either this A or B or C, because in these two cases the variation is linear, right? Because the variation is same as that of the bending moment. The stress is proportional to M at the bottom fiber, right? At the bottom fiber, the stress is proportional to M. So either this C is the answer or A is the answer. But what is the exact answer? So sigma stress will be equal to My by I. So at the point A, we can find out the stress. So stress will be equal to, at point A, stress will be equal to M. The value of M is known to us, 10 kilonewton meter. You can see here M. So this is 10 into 10 power 3. You can see here bending moment 10 kilonewton meter. Y is given to us 10 millimeter is the total depth. Then Y will be equal to 5 millimeter. So Y will be equal to 5 millimeter. So this is 5 divided by I, moment of inertia. What is moment of inertia? So I will be equal to BD cube by 12. So that will be equal to B, width is 10. D cube is a 10 cube by 12. So we can put here 10 into 10 cube by 12. So 10 cube to 10 cube cancel, 10 to 10 cancel, 12 5 are 60. This is 60 megapascal. So stress at point A is 60 megapascal. So this is the answer, 60 megapascal. So this is the answer, right? So variation of bending moment and bending stress is same in this case. That is linear variation. Value may be different. The variation is similar. That is linear variation. So from B to C, there was zero bending moment and zero stress was there. From C to A straight line variation was there, C to A. right? And it is increasing from C to A, and the maximum bending moment was at A, which is the fixed joint, right? And that was 10 kilonewton meter. And based on that, using this equation my by I, we have found out the maximum bending stress, because the bending moment was maximum, and that was a 60 megapascal. Let us take this question. This question was asked in GATE 2008. For the component loaded with a force F as shown in figure, the axial stress at the corner point P is, you can see here in the figure. We want to find out what is happening here at this P point. The stress, the value of stress at this P point, right? We have to find out. And this is the L-shaped component where a force F load is applied at this point, and the dimensions are given. This is 2b. If it is not clear, I am writing here. This is 2b, and this length is L. The length is L, and this length is L minus b. And this total length of the frame is L, right? So these are the dimensions given to us, and we have to find out what is the stress condition at point P. What is stress at point P? We have to find out the stress at point P. We have to find out. So this is the question, isn't it? I hope that this is clear. Now, here the force is F. This force is F. So it is producing a bending moment as well as a direct stress. The resultant of this force F will be two stresses will be there. One is the direct stress, one is the bending stress, right? So it is causing bending moment also, right? Whenever a load is applied here, whenever a load is applied like this at certain point, the bending stress will be acting at this point, and that bending stress will be given by F into L, right? Bending moment is there, due to which bending stresses will be there, and bending moment will be given by F into L. So similarly here, this force is acting at a distance of L minus B. So bending moment will be there, bending moment, and that will be force multiplied by L minus B. So this is the bending moment. So net resultant of this frame will be like this. I am making now. So this is our frame. Like this. This is the P point. This is a P point where we want to find our stress. And this force is producing a direct stress F and a bending moment like this, right? M, which has a value of F L minus B. So this is the case. So due to this bending moment at P point, there will be tensile stress due to this bending, right? So there will be two types of stresses will be there. Two types of stresses will be there. One is the direct stress. So due to F, there are two stresses, two types of stresses will be there. One is the direct stress, sigma d, given by force upon area, and another is the bending stress, sigma b, which is given by my by I, right? So this is our fiber. This is a rectangular section or square section. Square section is there, and two types of stresses will be there. So one is the direct stress, and direct stress is uniform. This is direct stress. And this is uniform. This is sigma d, which is equal to force upon area. And another is the bending stress, like this. This will be tensile on one end and compressive on other end, right? I'm showing tensile downward. So this is the stress condition. So this is the tensile stress. This is bending stress. This is my by I. Right. So on one phase, this is adding up. So at P point, this is adding, right? So stress at P point will be the sum of direct stress plus bending stress. The stress at P point will be sum of the direct stress and bending stress, because at P point, both the stresses are tensile. And if I take a point, another point Q, so sigma Q would have been sigma D direct stress, which is tensile, minus this is compressive. Here it is compressive. As you know that the bending stresses are on one side it is compressive, on another side it is tensile, right? So this is tensile. Direct stresses are tensile, and also this is tensile from this part, right? So at sigma Q, at Q point, the stresses would have been sigma D minus sigma B. Direct stress minus bending stresses, right? So we have to find out the stresses at point P. What is the stress at point P? So sigma P will be equal to, sigma at P will be equal to direct stress, which is given by force upon area, plus bending stress, which is given as my by I. My by I. So sigma P would have been F upon area. Area is, this is the area, cross-section area is given to us 2B into 2B, right? So this is 2B multiplied by 2B. This is a force by area plus M. M is known to us, force multiplied by distance, L minus B. This is F into L minus B multiplied by Y. What is the value of Y? Y is the distance of the outer fiber, this fiber. This is our Y. This is M. And Y is equal to B, basically the outer fiber, right? So this is B upon I, moment of inertia, that is B d cube by 12. So this is B d cube by 12. Solving it, and you will get the value as, that is F 3L minus 2B by 4B cube. So this is the answer, right? So what is the answer actually? This is D. D is the answer. So this is the answer, right? So what we have done here, that it was an L-shaped frame where the force was applied at the one end, and this force is causing two types of effects. One is the force itself, which is causing tensile and tension in the wire or frame, and another is the bending moment, right? Due to that bending moment, there are bending stresses, which is tensile on one end, compressive on other end, using the formula my by I, right? And the direct stresses are direct, and this is uniform throughout the section, and that is given by force upon area, right? Now there are 2 points there. They have chosen the point P. At P point, the nature of the direct stress is tensile, which is already there at all the nature of stress is tensile at P point, right? But we have to find out the stress at point P. So stress at point P will be addition of the two stresses, direct stresses and bending stresses. Direct stress is tensile, already there, force upon area, and bending stresses are my by I, and both are of same nature, tensile. Both are of tensile. I'm writing here. So that's why they are added up. So force upon area is given to us, that is 2b by 2b, and bending moment. And what is the bending moment of this? That is this, by this equation, is force multiplied by the distance. Distance is L minus b. From how much distance from the neutral axis or axis this force is applied, that is L minus b. F into L minus b is the bending moment. Y is the distance of the outer fiber of the material. So outer fiber of the material is at a distance of b. This is our y, and that is equal to b. So this is b by bd cube by 12. So this is b is the one of the width and d is the depth, and both are same because it is a square cross section, 2b into 2b. So 2b into 2b cube by 12. So solving it, you will get this equation, that is f into 3l minus 2b into divided by 4b cube, right? So this is how this question can be solved, right? So using these three questions, numericals, you can solve any type of questions of bending stresses. Bending stresses questions are of this type only. So I hope that these questions are you understand well, and so by this we can stop our class now. Right? So next week at same time we will meet with the another topic of the strength of material. So okay, good.